All right, in this video, I'm going to talk about elastic collisions and Diet Coke. You might wonder, what does Diet Coke have to do with elastic collisions? Well, you're just going to have to watch to find out. Okay, so first of all, let's define what an elastic collision is. An elastic collision is a collision where both momentum and kinetic energy are conserved. Let's just write that down. Both momentum and kinetic energy are conserved. Kinetic, let's try again, energy conserved. So let's just take a simple case. We have two objects, A and B. And let's say A is moving with the velocity VA, and B is moving with a velocity VB, and they collide elastically. So this is our before, and this is our after. And so we're going to use a prime notation to denote after. So I'm going to call this VA with a little prime meaning final, or after the collision, and here's VB after the collision. So by conservation of momentum, we know that the equation looks like this. The momentum before equals the momentum after. So that's going to be MAVA plus MBVB equals MAVA final plus MBVB final, right? Pretty straightforward. There we go. And kinetic energy, if the collision is elastic, then kinetic energy is also conserved. Kinetic energy, we remember, is 1/2 mv squared. So the kinetic energy conservation says that 1/2 MAVA squared plus 1/2 MVBB squared equals 1/2 MAVA final squared plus 1/2 M. Anyway, you get the idea. So let's write that out. 1/2 MAVA squared plus 1/2 MBVB squared equals 1/2. This is the boring part of the video. AVA final squared plus 1/2 MBVB final squared. Okay. Now the first thing I notice is I can get rid of all those 1/2s right away. Okay. So like so. Just multiply everything by 2, clears out all the 1/2s from this equation. Oops, got rid of that 1/2. MBVB final squared. Good. Okay, now I'm going to do a bit of algebra here. So I'm going to take this momentum equation. I'm going to get all the A's on the same side and all the B's on the same side. So the B's, I'm going to minus that over there, and the A's, I'm going to minus that over there. So it's going to end up looking like this. MAVA minus MAVA final equals MBVB final minus MBVB, like so. Then I'm going to factor out the M. That becomes MA VA minus VA final equals MB quantity VB final minus VB, like so. Now I'm going to do the same thing to the kinetic energy equation, because, boy, that just sounds like fun. Let's do lots of algebra. We love it. So MAVA squared minus, again, I'm going to minus the A's over here to get the A's together, minus the B's over there to get the B's together. MAVA final squared equals MBVB final squared minus MBVB squared. And then we factor out the M's. MA quantity VA squared minus VA final squared equals MB quantity VB final squared minus VB squared, like so. Okay, and it's at this point where I notice on the kinetic energy equation here that I've got this pattern that I recognize from my math class. It's called the difference of squares. So let me just refresh our memory on how the difference of squares works. If I have a squared minus b squared, I can factor that out to be a minus b times a plus b. That's a factorable quadratic, and it factors into this. Now, just to verify, let's just double check it. I'm in a FOIL. FOIL means I take my first terms, a squared, my outsides, plus ab, my insides, which is minus b times a, so minus ab. And then my lasts, which is minus b squared. Notice that the middle term disappears, and I'm left with a squared minus b squared. So a squared minus b squared is factors into a minus b times a plus b. Now, what that means here is this difference of squares can be factored out. I've got a MA, it's going to be VA minus VA final, and then quantity VA plus VA final, like so. This is just factoring that difference of squares into its factors, like so. Do the same thing on the right side. So I've got MB, and it's going to be VB final minus VB, VB final plus VB, like so, right? Okay. So we've done a whole lot of algebra. Now what's the point of this? I also remember learning in algebra that you can take an equation and you can divide both sides by the same number. So I'm going to take this big ugly looking equation here. I'm going to divide both sides by the same number. And the number I'm going to choose is this number, MA quantity VA minus VA final. Okay? Now I'm going to divide the right side by the same number. So the same number as this is this, MB VB final minus VB. You might see where I'm going with this now. So because of this equation here, conservation momentum, I know that this quantity is equal to this quantity. So I'm taking this equation and I'm dividing both sides by the same number. This number is the same as this number. Now, when I do this, the mass will cancel, and the VA minus VA final will cancel, the mass of B will cancel, and the VB final minus VB will cancel, leaving me with this, VA plus VA final equals VB final plus VB. A slight rearrangement of this is what I call the Diet Coke equation. So VA plus VA final equals VB plus VB final. This is the Diet Coke equation. Now, you might ask why I call it Diet Coke. Well, Coke stands for the conservation of kinetic energy. So technically, this big ugly equation here is the Coke equation. Conservation of kinetic energy, Coke. So this is the slimmer and diet version of that Coke equation. Now, what does this mean? This means that for elastic collisions, I can use my conservation of momentum and Diet Coke instead of using conservation of momentum and the full-on Coke equation, conservation of kinetic energy. This greatly simplifies the process of solving elastic collision problems. Let's do an example. Suppose I have an object here, 10 kilograms, moving at 2 meters per second to the right. And an object here, 2 kilograms, moving at 4 meters per second to the left. This is the before. And after they collide, I want to know what are the velocities. We'll call this A and we'll call this B. What are the velocities of both objects? Okay, so I can use conservation of momentum, right? M1v1 plus M2v2 equals M1v1 final plus M2v2 final. So here I've got 10 times 2 plus 2 times now. Direction is extremely important when doing conservation momentum problems. If to the right is positive, then to the left must be negative. So this is 2 times negative 4, and that's going to equal 10 times v1 final plus 2 times v2 final, like so. So this is 20 minus 8, 12 equals 10 v1 final plus 2 v2 final. Notice I have two unknowns, and you can't solve an equation with two unknowns unless you have a second equation. Now, because we're told that the collision is elastic, I know that I have conservation of kinetic energy, right? So I could use the full-on conservation of kinetic, right? I could say 1/2 times 10 times 2 squared plus 1/2 times 2 times negative 4 squared equals 1/2 times 10 times this squared plus 1/2 times 2 times this squared. And then I would end up with basically these same two unknowns. So I could solve this for V1, plug it in here for V1, have to square that, FOIL it out, get the like terms, do the quadratic formula, and solve for the answer. It's not really hard, but it is kind of time consuming. So if I do this with the Diet Coke equation, again, Diet Coke is the slimmed down version of conservation kinetic energy, only useful when used in conjunction with elastic collisions. Okay? Because the premise on which we built this equation was that kinetic energy was conserved and momentum is conserved. Right? The conservation momentum is what allowed all that stuff to cancel out. So this is a elastic collision problem, so we can use Diet Coke. So here we go. Diet Coke says V1 plus V1 final equals V2 plus V2 final. Okay? Which means V1 initial here is 2 plus V1 final, which I don't know, equals negative 4 plus V2 final. Okay? So now I'm going to go ahead and add 4 to both sides. So I have 6 plus V1 final equals V2 final. And now I can plug this in for V2 final right here. 12 equals 10 V1 final plus 2 quantity 6 plus V1 final. So what I end up with is 12 plus 2 V1 final. So 12 equals 10 V1 final plus 12 plus 2 V1 final. So I end up with minus 12, 0 equals 12 V1 final. Well, V1 final looks like it's 0. And if that's the case, if V1 final is 0, then V2 final must be 6. Right? Now, let's double check that. If this is in fact the correct answer, then it should work here, right? So here I've got 12, and that's going to equal 2 times 6 plus 0. That checks here. Let's check it with the full Coke equation, right? 1/2 10 2 squared plus 1/2 2 negative 4 squared equals 1/2 10, and we're saying that V1 final is 0 squared plus 1/2 2, and we're saying 6 squared. So let's just check and make sure left and right side are equal. This will verify that the Diet Coke in fact did work and give us the right answer. All right, so half of 10 is 5. 5 times 4 is 20. Half of 2 is 1. 1 times 16 is 16. So I have 36 over here. Equals. That's going to be 0 plus 1 times 6 squared is 36. It checks out. So you can see in this example that we could have done it using the full Coke equation, conservation kinetic energy, but it would have taken a little bit more time because we'd have to FOIL out, combine like terms, use quadratic formula, whereas Diet Coke was a very quick and easy way to solve this elastic collision problem.